This is a tank of oxygen, and the oxygen is going into this container through these rubber tubes, through the reducing valve to reduce the pressure, so it's just dribbling in there. I'm sticking it in a dewar now, which has liquid nitrogen in it. The liquid nitrogen is going to condense the oxygen. It takes a little bit of time for that to happen, so I'd like to get this started. There'll be a demonstration later in the show. And I can tell when all of it's being condensed because the balloon shrinks. And what will happen is Allison will watch the balloon, and she can't lift the dewar because she broke her wrist. So we might need some help from somebody to keep this under control. That would be you, Marshall, probably, since you're the responsible party here. And this looks like it's under control. Except there's no gas coming in that much. I think we're ready. Shall I just start? Yes, I just mentioned this. You're at IPFW, of course. This is the new science building you're in. It's a nice facility. Has all these gadgets. The gas is under lock and key, which Allison is setting up. And there are other safety things that tend to get in the way. You have to mess around with them. We're going to do a lot of things today, as you might suspect from what's up in the front. These are all demonstrations involving science and general physics and chemistry and stuff. I'm going to do some pretty simple stuff. We're going to start out with some simple stuff using liquid nitrogen. And we're going to do some pretty complicated stuff. I've got a demonstration that I will argue can't be done, and you'll be able to see it done. We're going to start out with a welcome. And what I'm going to do is to show you the properties of an element called phosphorus. What I'm going to do is to write with the phosphorus. These are pipe stem cleaners in a piece of glass tubing. With the glass tubing, I'm going to put the pipe stem cleaner right in it, and here's the solution of phosphorus. There are two kinds of phosphorus. They're called allotropes. That's probably a new word for you. You're going to learn a little bit here today, too. There's a new word right away. They're called allotropes. You're familiar with allotropes of carbon. You've heard of, everybody's heard of diamond, very expensive form of carbon. Everybody's heard of coal, very cheap form of carbon. And there's graphite, and nowadays it's not so popular anymore, but buckyball is another form of carbon. This is phosphorus, two kinds of phosphorus. What I'm going to do is to write with a solution of phosphorus on this piece of paper. And it'll just take me a couple minutes to get it organized here. There, I've written something on there. I'm going to show you what I said. And show you the properties of an element. Maybe. It's cool in here today, except I'm working up a sweat here already. Try and no. Here goes. Indiana University, Purdue University, Fort Wayne. And what you've seen, of course, you refer to as spontaneous combustion. This is yellow phosphorus, the highly reactive kind. It burns by itself. You know, if you want to burn something down after you've left, this is the kind of stuff to use. But of course, you can't get any, so you can't burn your school down. The other kind is red phosphorus, which shows up in matches and stuff. And I want this all to burn up because when I throw this away, I don't want it to go off after I've left either. Okay, welcome. We're going to start out with a series of demonstrations using liquid nitrogen. Nitrogen is the major component of the air. It's about 78%. You're sitting in a sea of gaseous nitrogen. Air, which is, it's got about 20% oxygen and a bunch of other things. States isolate argon from it. Maybe you've heard of argon. Well, sometimes called it inert, used to be called an inert gas. Now we refer to them as noble gases because they're not very reactive. If you take air and cool it down, put it under a lot of pressure, you can get a product called liquid air. If you take the liquid air, you can distill it like you can distill other liquids. Only you're distilling it at a very cold temperature, and you can get the products. You can isolate nitrogen, which is what I've got here in the liquid form, and oxygen, which is in that tank, which we're condensing to liquid oxygen for a later demonstration in the show. It's very cold, 320 degrees below 0 Fahrenheit. That's cold. Remember, water freezes at 32. Water boils at 212. Nitrogen boils at minus 320 degrees. So anything that it hits, which is warmer than 320 degrees, will cause it to boil. And the floor causes it to boil. And what happens is, when it hits the floor is hot, like a red hot stove. And gush all over the place. If it were a wooden floor, it wouldn't make as much noise. You would see little bubbles like you would pour the water on a red hot stove. Little balls of liquid nitrogen. Well, we're going to do some things. And these are pretty simple things. And probably you should be able to predict what's going to happen. To do things, we need to transfer it from one container to another. And I'm pouring it into what's referred to as a wide mouth Dewar flask. This one is a Dewar flask. 2 Dewar flasks have an inside container and an outside container, and usually some insulation or something in between. These are glass, and there's no insulation between the inside container and the outside container, but there's a vacuum in there. Vacuum, of course, doesn't conduct heat. So it's a good thing to keep things cold in. It's a good thing to keep things warm in. And of course, we're getting cold. It's cooling down. You can hear it hissing in there. And what's happening is the flask is getting down in temperature. It's then boiling away as it evaporates. What happens is the inside of the container cools down, and eventually it'll get down to about 320 degrees below 0. But still, you can still see through the mesh. That's the safety thing on the outside of this. You can still see it kind of boiling away. Later on, it'll show up a little bit better. We're going to put some things in there. And as I said, you should probably be able to predict what's going to happen. First thing is carnation. I just bought it at Scott's this morning. And you know what the properties are. They don't smell very good, but it's a nice flower for this demonstration. It has water in it, moisture in it. It's a biological thing. Anything which is biological has moisture in it. We're going to cool it down. Right now it's hot, right? It's going to cause the liquid nitrogen minus 320 degrees below, minus 320 degrees Fahrenheit. It's going to cause it to boil. So when I stick it in there, it's like a red hot poker. It's going to cause it to boil. The liquid nitrogen is boiling away. The flour is being cooled down. And it doesn't take much to cool it down to 320 degrees because there's not much mass there. And I'll show you how the properties are changed. One is you can tell it's cold because it's smoking. Well, actually it's the humidity in the air that's doing it. And the flour itself has changed. I'm using gloves to protect my fingers, of course, because I don't want to touch anything at 320 degrees below 0. There goes $1.25 in a flour unit. Just seeing the properties changed. Well, we have other things that we can put in there. And let's see. Ha! That wasn't very good. I don't think I'll do that again. I won't practice anymore. We're going to put one in. The liquid nitrogen. It's going to cool down. It's boiling away because it's hot, of course. Warmer than 320 degrees below zero. I'm going to put something else down in there, another biological thing. This has moisture in it. And those two things take a while to cool down, so we're going to just let them go. And there are other things we have here, easy things to do. This is rubber tubing that we use for transporting gases and liquids. There's not much mass for the rubber tubing, so it won't take long to cool it down to 320 degrees below zero. And you can see how its properties have changed. Doesn't take long because it's cold. It's real cool stuff. And in this case, you can see it frosting up. It's picking up moisture from the air. Of course, you know what frost is. And since the tubing is so cold, it's picking up moisture from the air. And it's looking like. This section wasn't down in the liquid nitrogen, of course, so it's the usual stuff. This has changed its properties because of the cold temperature. You shouldn't be surprised with that. We can tell it's still boiling away, so it's not done. The banana isn't down to temperature, or the ball isn't down to temperature, so we'll just set this aside, let it work for a while, and move to another piece of equipment, which again is a Dewar flask. This is a glass Dewar flask. We call this a narrow neck Dewar flask, and the reason it's a narrow neck is because I'm going to do something different with it. But you can see the construction. There's an inside container and an outside container. It's sealed together at the top here. There's a little spigot on the end, and what was done when this was made, the air was sucked out with a vacuum pump. There's a vacuum in between these two spaces. And again, vacuum doesn't conduct heat. It's better than air. It's better than any insulation you can have. So this is a good Dewar flask. The problem with it is we're going to put some liquid nitrogen down in there. The problem is the narrow neck, and it's hot, of course. So when the nitrogen goes in there, what's going to happen is it's going to boil because it's so hot on the inside until the temperature gets down to 320 degrees below zero. But I'll get some in there. It's not that much of a problem. You can see it gushing all over the place. A little bit more. There we go. It's boiling away in there. What you see coming out, of course, is not the liquid nitrogen. The liquid nitrogen, the gaseous nitrogen, you can't see. You're looking through it, of course, right now. And well, I let most of it boil away. Usually it blows for a much longer time, and I froze my whistle. What's happening is the gas is coming out, of course, blowing the whistle. At the same time, the inside of the container is being cooled down to 320 degrees below zero. And you can tell when it gets down there because there's not much gas coming out. And the reason is because there's not enough heat to cause the stuff to boil away. Well, we're going to do other things. With this, Allison is getting the next piece of equipment ready. I'll take one end. She'll take the other end and connect it to a vacuum pump. I'm attaching this thing to, this is just a valve, which when like this, we have a closed system. It's a completely closed system. And we can see how much pressure is building up in there. When I open it up, ooh, there's hardly anything coming out at all. It means the temperature is down to about 320 degrees below zero. And of course, when it was coming out, gushing out, I couldn't put this thing on there, which is blow it out. Allison has a vacuum pump she's ready to turn on, and we're going to pump on this stuff. I'm ready. And what's going to happen is we're going to cause the liquid nitrogen to boil away faster than it would just at atmospheric pressure. Pumping the gases away, the inside of the container is the pressure is being reduced on the inside, causing the liquid nitrogen to boil. When it boils, of course, the heat has to come from somewhere, and we have a container, of course, that protects it, and the only place the heat can come from is the liquid nitrogen. So we're working at it. What happens is, since the heat comes from the liquid nitrogen is cooling down. And as you cool the liquid nitrogen down, you can eventually reach the melting point of nitrogen. So what we're doing is, we're starting out at 320 degrees below zero. We don't have to go very much further down. I think it's like 16 degrees before you reach the melting point of nitrogen. So we started at 320 degrees, temperature dropping, and when it's cold enough, there will be a solid in there. And the hot spot is the liquid, which is kind of convenient because that's what we want to cool down. If it's liquid, of course, that means it's not down to its freezing point. Yes, and that's where most of the heat is going to come from. And it's getting down there. I'll shut this off. We'll shut the pump off. And remember how we started. Nitrogen is the major component of the air. So if you want, you're looking at a chunk of air in there. It's kind of frothy because it was bubbling and boiling while we were cooling it down. So it's not like a snowball. It's round like a snowball, but you can't get in there with your fingers because it's under vacuum. And in fact, what I'm going to do is to open it up. And what's going to happen when I open it up? It's under vacuum. It's going to suck hot air in, and you will see what you can call it a variety of things. A phase transition, a change of state. We're going from the solid state to the liquid state. We just warmed it up enough to melt the solid nitrogen to convert it back to liquid nitrogen. It's a little bit cloudy now because when we opened it up to the air, we sucked in oxygen, of course, moisture. There's moisture in the air all the time. Carbon dioxide, you're breathing out carbon dioxide and those kinds of things. So it's picked up those things. We no longer have a nice clear liquid in there. And you remember I didn't touch the flour, but I can do this if I'm careful, because my hand is like a red hot stove. And what happens is when the liquid nitrogen hits my hand, there's apparently enough gaseous nitrogen to protect my hand from the liquid nitrogen, but I won't touch anything that's solid. And in fact, I'm very careful with this too, because I don't want my hand to get like the things we've been cooling down here, of course. Okay, well, our banana is cooled down. Our ball is cooled down. And thank you, Allison. Let's get the ball out first. Yeah, that wall. You can catch it. Put a glove on. I'm going to throw it against that wall over there again. And if it bounces, I'm not very good at this, so if it bounces towards you, don't catch it because you don't have a glove on. Did you expect that? Yeah. A banana. Moisture in there. You should expect what's going to happen to this too. And what we've got is a block of wood, a nail, a banana, and property. good banana either. I like them when they've got brown spots on them. But I'll take a little bite. This end was sticking up. This end was down on liquid nitrogen. And it's cold, but it's not frozen. Of course, as you go down, it's going to get tougher and tougher and tougher. And the flavor isn't there for this one. One bite is enough. And we're going to get rid of it. It's a fruit, and when you freeze fruit, what happens is fruit, when it thaws out, gets mushy. And these get real mushy. So there goes the banana. One last thing for the liquid nitrogen. How are we doing now? I'll do it. Do we have enough?
Yeah.
I mean, is there enough oxygen?
Oh, no, yes.
Okay. Just a little bit more in there for the last demonstration involving liquid nitrogen. 320 degrees below zero is cold. And what I'm going to do now is to show you one of the properties of gases. One of the properties that you're probably already familiar with. There, I've got a container with a gas in it. The gas is mostly nitrogen. It's got some oxygen, not quite as much as the air, because by breathing it in and using it up, I've contributed some carbon dioxide in here and some moisture, vapor, water vapor, and banana flavor. I always point that out. But it's a sealed container of a gas. And what we're going to do is to cool the gas down. And you probably already know, if you take gas and warm it up, it expands. And if you cool it down, it shrinks. I'm going to cool it down to 320 degrees below zero. You need a net here. I'm not going to put my fingers down in there because I don't want to take any chances on that. Bouncing off my hand is one thing, but fingers in there is another. We're going to cool this down to 320 degrees, and I can tell when it's down there because it shrinks to just about nothing. I've taken it out, and what happens is we're at room temperature now, and the gas is going to expand. And the rubber has to thaw out. And what's going to, there's also a little puddle down in the bottom. You can see where the water vapor, steam, whatever you want to call it, is coming up from the end. That's probably the oxygen which blows away later. And what happens when it warms up, what's going to happen is it's going to fill the balloon back up to its original volume. And of course, we can go back and forth and back and forth. Okay, well, so much for liquid nitrogen. Most of that stuff you probably should have expected. But the 320 degrees to shrink that down to nothing might be a surprise to you. It should give you a better indication of what 320 degrees below zero really is. Well, we're going to switch now and do some chemistry. And we're going to start out with a demonstration involving a solution of an indicator dye, a pH indicator dye. If you haven't heard the term pH before, well, you might have heard it on television, actually, as in pH balanced, pH neutral. Those are phrases which are sometimes thrown out in television. And what we have, pH has to do with acids and bases. I have a container of acid and a container of base. They're both dropping containers. And the inside there's a little medicine dropper, which makes it convenient for measuring a drop or two. I'm going to put a drop in here and give it a shake. Another drop in two, give it a shake. Oh. Well, I'm not where I want it to be yet. Whoa, there, I've added enough. Well, fighting me. There's an indicator dye in there. I'm adding base to it now. And if I get enough base in there, we will have what's called a basic solution. When the solution is basic enough, it'll remain pink. And there's some stuff floating around in there too. What I usually do is leave this from show to show and never clean it out, but it looks like I'm going to have to clean it out. I don't want things growing in there. And if you add enough base, it should stay pink. And it seems to be fighting. They're staying pink. Maybe. It's basic. When it's pink, it's basic. Well, it's losing. I can help it. A drop of acid, it'll be all gone. This is an indicator, a pH indicator dye, which is clear and colorless when it's acid, which it is now, and pink when it's basic. Well, that's enough of that one. We're going to move to a little bit more complicated one. This one you can tell is different because it's already red. But we're going to do the same thing. And I didn't correct this one either, but there. It's a little bit dark too, isn't it? What's the color? Yeah, would you call that green? I'm adding base to it. So it's green when it's basic. We can go back and forth. A little bit of acid in there. We'll make it on the acid side. We can go back and forth. These are called reversible indicator dyes. I'm going to add a... Well, there's too much dye in there, I think. But if I swirl it around, you can see what color it is. What would you call that? Green? I'm going to add something else to it. And what I've been doing here, of course, is I've added some stuff, given it a shake, and the colors have changed. Given it a shake, and the colors have changed. Oh, well. What color is it? Is it acid or basic? Right now it's acid because it's the red color. I'm going to add some more base to it, give it a shake. Is it acid or basic? I'm not going to add anything more to it. So what's going to happen is it's turning acid. This is called, actually if I added enough base it would be kind of purple. And then it'll go to a blue and then a green and then a yellow and then an orange and then finally it ends up as a red. And those of course are close to the colors of the rainbow. This is called a rainbow clock reaction. Rainbow because of the colors, clock because it takes a little bit of time before you see evidence of the reaction. Next we have another clock reaction, and there are three of them that are set up to be exactly the same. I'm going to show you some, well, we're going to change the last one to show you how we can control chemical reaction. Again, as a clock reaction, when I dump the two things together, that starts the clock. What I'm going to do is to dump them together and start counting. 1, 2, 3, 4, 5, 6, 7, 8, and this again is a clock reaction, a two color change clock reactions. The colors of Purdue University. I always point that out. We have three of them. I'm going to do another one exactly the same, so this should perform exactly the same. If you make up the solutions exactly the same, and the temperature is the same, and all of those variables are the same, they should perform the same. 1001, 1002, 1003, 1004, 1005, 1006, 1007. It takes about 7 seconds before it goes. The last one I'm going to change. And you know about some things about chemical reactions. You probably already have a feeling for some chemical reactions. You probably already feel that if you warm things up, things go faster. If you cool things down, they go slower. And in fact, that's why you have refrigerators. You cool things down, so those biological reactions go slower. And we could warm this up or cool it down with ice, but it turns out to be convenient to dilute it. And you might have a feeling for what goes on there. What's going to happen is we're going to modify this reaction, and what's going to happen is it's going to go slower because of the dilution. And if it goes slower, what's going to happen to the time that it takes to change colors? You should be able to figure that out in a flash. We're going to count the same way. 1001, 1002, 1003, 1004, 1005, 1006, 1007, 1008, 1009, 10, 11, 12, 13, 14, 15, 16. A little bit twice as long for the amount of water that we added. Now, Purdue University, and there are probably IU people out there. I can't make the IU colors, but I can get rid of the colors of Purdue University. And it's more fun to dump the black into the clear and watch what happens. Pour the black right in there. There go the colors of Purdue University. They used to give me a check every month, but they don't anymore, because I retired. Well, that was solution chemistry. We're going to switch now to a few compounds that have energy associated with them. And as I said when we started, I'm going to do some things that you might be familiar with and use some things that you might be familiar with. This turns out to be a compound that, well, you're getting to the age where it might be useful to you. The compound is called benzoyl peroxide. It's used in a medicinal called Oxy-10, except this is pure benzoyl peroxide. Oxy-10 has 10% benzoyl peroxide. It's used for zits, pimples, and things like that. Well, benzoyl peroxide is also a very powerful oxidizing agent. And what's going to happen, let's see, for the camera, you probably want to be up in here somewhere. I'm going to add to benzoyl peroxide a very powerful oxidizing agent, something which is very easily oxidized. Just a couple of drops in there. And what happens is, when you get something which is a very powerful oxidizing agent in the presence of something which is very easily oxidized, you'll get a reaction like this, like this, like this. With the, oh, golly gee. Didn't get a beaker out. The next demonstration. Oh, I'm going to use that. Right. The next is, I'm going to use a couple of compounds. And one of the compounds is in here. This is called ethyl alcohol or ethanol. You might have heard of it. When you're 21, you might drink it, actually. This is the kind of alcohol that shows up in alcoholic beverages. This material is a calcium salt. It's calcium acetate. Calcium acetate is, well, the ion, metal. The element is, of course, Q for throwing bones and teeth. You've heard of that before. Drink milk so you get your calcium. This is the calcium salt. Ethyl alcohol. I'm going to pour these two things together and make something that if you're a camper or if you entertain a lot, you might be familiar with. You're going to dump them in together, and you can see things are happening in there. And what has happened is it's turned to a solid. The material that I have in here is sold commercially as a product called Sterno. Or if your parents have a fondue set, you might buy solid fuel in a can. This is the stuff. I just made it for you. What we're going to do is to show you the energy in this. I'm going to carve out a little bit of the stuff. It's kind of waxy stuff like that. I'm going to put it in this dish here. Get this out of the way. I'm going to burn that. I'm going to ignite it. But I'm going to ignite it in kind of a neat way. I'm going to ignite it with this candle, which I'm going to ignite with my magic wand. And there's my magic wand. There's the candle. Just touch them together, and that's going. I'll touch that to the ethyl alcohol. It's burning away. The reason ethyl alcohol is used for a variety of things is used for gasoline. Although you don't hear much anymore. It's called gasohol. You might remember that. It's used for fondue sets because it burns with a nice clean flame. You can hardly see it there. And Allison is ready to turn the lights out. I'm going to fish out a little aluminum dust. 4th of July is coming up, and when the 4th of July comes, and you look at the sparklers, if you see white sparks coming out like that, it's probably aluminum. If you see, I think you can get a couple of kinds of sparklers. If you get another kind, you might see just gold sparklers. This is just iron dust is really all. So when the 4th comes and you look at all that stuff, you know some of the chemistry which is happening. Okay. Next. We're still looking at energy. All of these things have energy associated with them. We have here a container. It's a plastic container, has a wire coming out of it. Actually, there are 2 wires in there, and there's a gap in between. And I don't know if you can see it from that far away, but there's a gap between. It's getting kind of old. I think we're going to have to get another one. I'm going to put some more ethyl alcohol in there. And I'll just squirt some in there from this dropping tube. We're going to close it up. I don't know what seed is that. Don't get in there. Let me do this first. We're going to close it up there, and I guess I'll come around in the back. Allison has it already. This thing is called a Tesla coil, and she's plugged it into the house current. When I turn this knob down here, it'll start making noise. And what happens is there's a very high voltage at that end. And you can see the high voltage. And to further show you that, this thing is called a discharge tube. It's got neon in it. And well, with the lights out, I don't even have to touch it. You see. That's how you make neon signs. You take glass tubing and bend it around to write open, beer, whatever you're writing. Put neon in it, and with high voltage, you can make it light up. This is a sign saying I. Well, we have this thing still. And if you put all that together, you have an idea what's going to happen. Where did it go? There it is. There's energy in that system. Yeah. Okay. Here. And here we go with this. We'll see that shortly. I think I'm going to use the torch for... Okay. We'll move this back when we get there. I'll explain that in just a flash. The next demonstration involves, well, everything that is involved in this demonstration you're familiar with, probably. Wire gauze, wire, penny at the end. There's nothing there. A container. We use beakers, of course. The compound I'm going to use is isopropyl alcohol, which you might have at home, as isopropyl rubbing alcohol, which is 70%. This is 100%. I'm just going to pour some in here for the demonstration. I'm going to we need a lot of heat, and those Bunsen burners aren't quite hot enough. So I'm going to use this torch. Okay. What I'm going to do is to warm up the penny until it's red hot. It doesn't take long with this torch. There we have a red hot penny. And you know, of course, if you take the source of heat away, it doesn't take long before the heat radiates away and it's no longer red hot. What is that, about 10 seconds or so? I'm going to warm this up a little bit. This is, again, isopropyl alcohol in a beaker. We'll warm it up a little bit. Get the penny red hot again. Put it down in the beaker. And remember, it was only like 10 seconds before it cooled down to where it wasn't glowing anymore. It's still hot. All we've got is a red hot penny and isopropyl alcohol. I warmed it up so there's more vapor in there to get onto the penny. And it's still red hot. There's a reaction going on. It's called a dehydrogenation reaction. We take isopropyl alcohol and dehydrogenate it. And if you have, well, when you get to Latin, you can figure out those words. D means you're taking it away. Hydrogen means it's hydrogen we're taking away. The ending ation is the process of taking hydrogen away.
How long will that go?
It'll go for some time. In fact, I think we can probably pass it around today, but it's getting hot. And of course, it's red hot, and the beaker's going to get hotter and hotter and hotter. Right now, it's not so bad, but when it gets to the end, it'll be hot. Don't touch the metal, because heat, metal conducts the heat. Hang on to it by the sides. Don't dump it on you. If you get isopropyl alcohol on you, it's rubbing alcohol, remember, so that's not bad. But it's a red hot penny. That'll brand you. It'll be branded with Lincoln's face. Slide it down. I like this real well because it's so simple and so neat. Don't you think it's neat? Somebody go like this. Thanks. Okay. penny. The next demonstration involves money. Back in the old days, when there were kings and jousting and whatever, there were alchemists. And the alchemists were always trying to convert base metals, mostly lead, into gold for the king. And the king would always hire these guys because if they could do it, he would have more gold than what he's got. It's called transmutation. And it used to be years ago when we taught chemistry, we'd say, you can't do that. And now we say, you can't do that chemically. But of course, you know that atomic processes involve conversion of one element to another. You've heard that before. Well, I'm going to convert one element to another in this case. I'm going to start out with 3 pennies. One we're going to keep for a standard so we can compare it as we're going along. The other 2 we're going to modify. And we're going to modify it in that container that I just moved back. And this is going to take a little while. And we'll let Allison tend it while I hear it. There we go. There, that looks stable. We're going to take 2 of the pennies and put them in this solution, which I previously prepared. We're just going to drop them down in there and save this one. And now we're going to get that to boil in. And what's going to happen is we're going to change the pennies. And eventually we'll fish them out, and I'll show you how they change, and then we'll go on with it. That's going to take a while. While that's going on, we're going to move to the next demonstration, which again involves a lot of things that you're familiar with. The first thing that goes in there is called hydrogen peroxide, which you might have had on you. Except if you had it on you, it probably was 3% hydrogen peroxide. And you use it to put on a cut or something that's supposed to kill the germs and stuff. This is 30% hydrogen peroxide, and you don't want to get it on you because it hurts. It'll bleach your skin, it'll make it immediately white, and it'll hurt until you wash it off. This is another ingredient that you might be familiar with. Probably should be more familiar with. You should help with dishes at home once in a while. This is just food coloring. I don't want to mix that up. This is just food coloring, and the only reason for adding that is to make it pretty. There's no value in food coloring. But that aesthetic qualities. Last ingredient. There's going to be a reaction. Remember, we're looking at things that have energy associated with them. So here goes the last ingredient. There's energy in that stuff. And let's look at our pennies. Well, they're not quite done. besides that, I can't see them in there. They're not quite done. We'll let them cook a while longer. While we're waiting for those to get done, we'll move on to the next demonstration, which, remember we set this up a long time ago? This is liquid oxygen. Remember, this is a tank of oxygen under high pressure. We bled it out. There we go. We bled it out, cooled it down to liquid nitrogen, and condensed the oxygen. And you'll note it's blue. And there's a little bit of, looks like ice in there too. And what we're going to do is to use the liquid oxygen, and I'm going to transfer it into another container because I want to get in there. There's the liquid oxygen boiling away because that container is hot. And we're going to use this thing for the demonstration. I'm going to do it a couple of times for you. There, I'm running a reaction for you. What I'm doing is grinding it up, mixing it with saliva, swallowing it, going down in my stomach. I'm breathing in oxygen. This is hot, liquid oxygen, and of course I'm putting a hot donut in there. So what happens is it causes the liquefied gas to boil, which cools the donut down. And get me a match ready, would you, Allison? And what should happen, of course, is that the piece of donut should be saturated with oxygen. And I'm going to show you the same reaction with this piece of donut that's going on in my stomach right now. What's happening is, of course, I'm getting the food energy from that piece of donut. And I'm going to make sure that it's saturated. There's a fire extinguisher right down in front there. Hey, that was a good one. Small piece of donut. Calories. Energy. There's a lot of energy in that small. It's not even all burned up. But there's still a lot of stuff left there. And of course, there's a lot of donut left. Imagine if we burned a whole donut, how much flame we would get. And maybe that'll give you a better appreciation for calories in donuts, at least. Well, let's see what's happening here. I fished the thinny out. Ooh, it looks pretty good. I'll fish the other one out. And I want to dry them off a little bit and then show you what we've done. Remember, we put 2 pennies in there, left one out for the comparison. And here's what's happened. New penny there is still a copper penny. But remember, the alchemists wanted to make gold, and we have silver instead. At the moment, we have silver. 2 silver pennies and a copper one. I'm going to change one of these to gold, right in front of your eyes. do that, I need the Bunsen burner. And what I'm going to do is to take one of the silver pennies and heat it up. And what's going to happen is, right in front of your eyes, it's going to change to gold. Maybe. Oops, there it goes. Did you see it change? Now, of course, it's hot, of course, because it's right in the flame. Where did our other two go? So I'm not going to hang on to it with my fingers. I'm going to leave it in the tongs. But now we have the original copper, silver, and hot gold, of course. It's gold. Would I lie to you? Does it look like gold? Mm-hmm. Right. Copper, silver, and gold. And of course, the alchemists never were successful in converting base metals to gold. Well, maybe. Okay, where are we? We're getting close to the end. Well, I didn't put this one together. Yep, they're close. We have 3 containers of stuff here, and what I'm going to show you is the most sophisticated demonstration that we've got here today. Takes 3 solutions. It, again, is a clock reaction. There's a second solution going in. The third solution starts the clock. In this case, of course, it's a different one than what you've seen before. There goes the clock. Yellow. Oh, not blue. Did you see it? Well, if you didn't see it, what I'm going to do is to clear it up for you. Clear up. And do it again. Yellow. Blue. Did you see it that time? Well, if you didn't, what I'll do is I'll go through the whole process again, clear it up, turn it yellow, turn it blue. Now, this is sophisticated stuff, and the analogy that I always use is kind of like going over a reaction over and over and over again. You go through the process over and over and over again. It's kind of like in real life, it would be like throwing a log on a fire, burning it up, and then somehow retrieving the log and burning it up again, and then somehow retrieving that log and burning it up again. And of course you can't do that, except there it is. Yellow needs to be stirred up. Ooh. And we stir it up in a neat way here. This is called an oscillating clock reaction. Oscillating because it goes back and forth. Clock because it's time to go. That's sophisticated chemistry. When the guy that came up with it years ago tried to publish it in the recognized, reputable journals, the chemists that were the editors wouldn't accept it because they said, you can't do that, and nobody tried. So he published in some obscure journal first. Neat stuff. That's sophisticated stuff. Well, we're at the end. I don't think I missed anything. The last demonstration involves a bunch of solutions here, and again it's a clock reaction, so when I dump one thing into the other, it starts the clock, and we call this a patriotic ending because of the colors that it produces. Like, well, it's kind of red. Yeah, kind of white and blue. The white ones are the hardest ones to see. That's clear now. And, well, there it is. It didn't do very much, but it's trying. Red, white, blue, red, white, and blue. That's my show. I hope you enjoyed yourself. I hope you learned a little bit. Thank you very much. When you come to college, don't forget, the chemistry department is up at IPFW. It's pretty good. Cheap too if you live in town.
What was the last ingredient you put in that green? You didn't mention.
This thing?
Yeah.
It's potassium iodide, saturated potassium iodide. What that does is releases the oxygen from the nitrogen peroxide.
Thank you. I'm going to take something like this. Cassie. No cancer. We know who will be the
Well, go sitting home, and every time you look at it, you can think of IPFW. Yeah, it is. What? What? I didn't. There's Ben too. Well, it's him developed last year. Do you have tennis from today? You guys get paid to come here. A goat penny, Richard.
Oh my gosh, you're kidding.
Still going, isn't it? Still coming. you again. We'll move on. Thanks for coming. Come back when you hold up. We're gonna come back when you want to go to college.
Oh, really?
Only one piece. One piece. Fine. Now I should know you like that.
So, this extension office, you know,
She's fine.